Good afternoon, class. Here's chapter 4, application of derivatives, section 4.1, maximum and minimum values. So we are going to cover in this chapter maximum and minimum values, how derivatives affect the shape of a graph, optimization problems, antiderivatives. Starting with the differentiation formulas and their definition. dy dx is limit of delta y over delta x as delta x approaches 0, or f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. Definition of an E is the limit of 1 plus 1 over n to the power of n as n approaches infinity, or E is a number such that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. Various rules, such as the power rule, the derivative of x to the power of n is n x to the power of n minus 1, or trigonometric functions, such as the derivative of sine is cosine is negative sine, and so on. And other theorems involving the sum and difference and a constant multiple, product and quotient rules, composite function resulting in the chain rule, as well as the extended power rule. Exponentials, basically the derivative is itself, and it depends on the base and whether we use the chain rule or not. Logarithmic functions and their derivatives. Also, if you have y equals f of x, this is the curve, as you go from one point to the next, for example, P to Q, run along the x-axis, you cover delta x or dx or bp, this distance of dc or bp. And the rise is what you cover along the y-axis for the curve is delta y, which is this distance, bq. But along the tangent line is this distance, which is dy. And sometimes we use dy to approximate delta y. So delta y is f of x plus delta x minus f of x. F of x plus delta x minus f of x. And so you move it around, f of x plus delta x becomes f of x plus delta y. Since f prime of x is dy dx, dy is f prime of x dx, and we can replace this with dy, and that becomes an approximation. F of x plus delta x is approximated to f of x plus dy. Linearization simply means find the equation of a tangent line, and you can use the point slope, y minus y1 equals n times x minus x of 1 on this pair, and come up with the answer. What is important to understand is the following. At this point P, if you plug in the x coordinate into the original function f of x, y equals f of x, or the tangent line, the result is the same for the y. However, when you plug numbers nearby through the function y equals f of x versus the tangent line, they're different. But if it's close, tangent line is a good approximation of it. And now, section 4.1, maximum and minimum values. Definition, critical points, or short, CP. A critical number point of a function f is a number c such that f prime is 0 or f prime does not exist, DNE. For example, we want to find the critical numbers for f of x equals x cubed plus 3x squared minus 24x. So what is the process? Number one, find f prime of x. So I'm going to differentiate this. To find f prime of x, I get 3x squared plus 6x minus 24. Number two, I have to set this equal to 0. To set this equal to 0, I'm going to factor the 3 out. I get 3 parentheses x squared plus 2x minus 8, and that's equal to 0. To continue working on step 2, I need to factor this. I want two numbers. The product is -8. The sum is +2. In other words, -8, the product, +2 is the sum. So two numbers. So you look at factors of -8. And because the product is -8, then one of them must be positive, one of them negative, +4, -2. This, you set it equal to 0, you get x equals -4, and this one, you get x equals 2. Those are the two answers. The third step, f prime of x does not exist. When we look at f prime of x, because it's a polynomial of degree 2 and it exists everywhere, meaning the domain is all real numbers, this doesn't produce any solutions. So we have two critical points, x equals -4, x equals 2. If by any chance they want them in the form of a pair, you have to put them back, -4 evaluated, number 2 evaluated, and you get the two pairs accordingly. Now, formal definition, maximum or minimum points on a curve. Local, also known as relative extreme value. Extrema is the plural of the Latin extremum. A local minimum is the minimum value within some open interval. Local minimum occurs at the point C in an open interval of A to B in the domain if f of c is less than or equal to f of x for all x values in the open interval. A local maximum is the maximum value within some open interval. Local maximum occurs at the point C in an open interval A to B in the domain if f of c is larger than or equal to f of x. Compare the two for all x values in the open interval. So in some open interval, this is a local minimum, this is a local maximum, local minimum, local maximum. In other words, peaks are considered local max, valleys are considered local mean. Absolute, also known as global extreme values or extrema, are either maximum or minimum points on a curve. Absolute maximum occurs, absolute minimum occurs at a point if f of c is less than or equal to f of x for all x values in the domain. Absolute maximum occurs at a point c if f of c is larger than or equal to f of x for all x values in the domain. In other words, the difference between these two, this happens in some open interval. In this case, both of them happen in the entire interval. So if we look at these two cases, local mean, local max, local mean, local max, local mean, local mean. So peaks and valleys are always considered local. Then you observe that this one not only is a local minimum, is also an absolute minimum because no other point has a smaller y coordinate. Whereas this one is not only a local max, it is also an absolute max because no other point has a larger y coordinate. So that's why we have that. So I hope everybody's okay with the concept. Local or relative extreme values. According to Fermat's theorem, if a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime must be 0. So as we look at this one, please understand this is local mean, this is local max, this is local max. This too, because it's smooth curve, if you draw a tangent line at the peak or valley, it becomes a horizontal line. Every horizontal line has a slope 0. In essence, f prime becomes 0. This one is a local max, and f prime does not exist because it's a sharp corner. However, in the entire domain, because no other point has a larger y coordinate, it is also an absolute maximum. So if f prime exists, it must be 0. Local extremes in the interior of the function occur where f prime is 0 or f prime is undefined. F prime is 0 or f prime is undefined. Maxima and minima of a function always occur at critical points. So if you have a maximum or minimum, then you have a critical point as well. But critical points are not always maximum or minimum values, so not the other way. It may be a critical point, but it may not represent anything. That's the idea. We're going to look at a very simple example. Extreme values can be in the interior or the endpoints of a function. Endpoints can never be a local extremum. That's important to understand. So we're going to look at y equals x squared, a parabola that opens up. As you know, it's a polynomial of degree 2 with the domain being all real numbers. So this is an open interval. So I hope you recognize this as a local minimum at 0, 0. And since no other point has a smaller y-coordinate, it's also an absolute minimum. So this point is an absolute minimum as well as a local minimum. It's a bad. But we don't have a local or absolute max. We don't have that. As far as writing, by the way, absolute minimum equals to the y-coordinate. Okay, everybody? So this one. Now you can say at either x equals 0 or the pair 0, 0. Now, which one just depends on how they want you to write it. Now, what happens here, we look at the same function, but we restrict it from 0 to 2, which is clearly a closed interval. That means the endpoints are included. Now, clearly this point, 0, 0 is the absolute minimum, and this point 2, 4 is the absolute maximum. By the way, how did we get 4? If you put 2 into this function, you get 4. So this one, we've already discussed that. For example, you would write this. Absolute max is 4. At either you write the pair or the x coordinate. X equals to either. And we don't have any local. We don't have local extremes because the endpoints can only be absolute. So a closed interval and a continuous function has both of them. Now this one is half open, half closed. So what happens is that this is not included, so we don't have a minimum. But we still have the same maximum. So we still have the absolute maximum. So there's no local extremes, okay? Now let's make it completely open on both sides. So this is an open interval. So the endpoints are not included. So we have absolutely nothing, which means no minimum, no maximum, no local extremes, nothing. So in essence, it gives rise to the following theorem, extreme value or closed interval theorem. If f is a continuous function over a closed interval of a to b, then f has a maximum and minimum value over that interval. So there are two things that we need to pay attention to. The function must be a continuous function, and we are looking at a closed interval. The endpoints must be included for this to work. Then when that happens, maximum and minimum can be anywhere. In this case, both of them. This is the absolute max, this is the absolute minimum. Both of them at interior points. So maximum and minimum at interior points. What about this one? Max mean. So maximum and minimum at endpoints. What about this one? We have the max here, we have the mean here. That means maximum at interior point, but the minimum at endpoint. So we have one of those three situations, which means no matter what, as long as the function is continuous and the interval of interest is a closed interval, we do have both absolute maximum as well as absolute minimum. That's a very important theorem. And so having said that, to find absolute max and minimum values by extreme value or closed interval theorem, we do the following. Number one, find the critical point CPs and evaluate the function at those points, the function at CPs. So we find the critical points, evaluate the function. Also, find the values of the functions at the endpoints, f of A as well as f of B. We want to evaluate those two. And finally, the largest value is the absolute max, and the smallest value is the absolute. Very straightforward, everybody. So this is repeating what we just said. The extreme value, also known as a closed interval theorem. If f is continuous over a closed interval of a to b, then f has a maximum and minimum value over the interval. So that's the theorem of interest. So having said that, let's look at this very simple example. Example 2. Find the absolute max and mean value of function f of x on the given interval. F of x is 1/3 x cubed minus 9x, and the interval, the closed interval of -6 to 0. Here's the process. But before we go over there, it's important to know you have to mention what type of function you have, what is the domain of the function on a regular basis, and whether or not this works, this given interval. So to do so, I'm going to remind you of a couple of things. Number one, all functions are continuous in their entire domain. I want to elaborate on that. If you look at all the all different types of functions we've seen in algebra, such as polynomial functions, rational functions, logarithmic functions, exponential functions, trigonometric functions, we remember the graph, we should, and therefore we remember the domain. And as long as we mention the domain, that means the function is continuous in that domain. That's the meaning of a domain. So in the case of a polynomial functions are in the form of f of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus a sub 1x plus a sub 0. A sub 0 is the constant, and a sub n x to the power of n is the leading term, and a sub n is the leading coefficient, where each a sub I is real. A sub n can't be 0 because we say it's of degree n, and n is a whole number, 0, 1, 2, 3 to infinity. Domain are real numbers. So what are we dealing with here? We are dealing with a polynomial of degree 3. Therefore, the domain is all real numbers. Because the domain is all real numbers, and because the interval of -6, 0 is part of the real number, all real numbers, therefore it's continuous in that domain. So we write f is a polynomial of degree 3. is continuous on the interval of negative to positive infinity, and therefore is continuous in the given interval, and you just write out the given interval. Now that we have justified the use of the extreme value theorem, we are going to apply that step by step. Number one, find CPs. That means go with f prime of x. So let's go with f prime of x. So what is f prime of x? 1/3 times 3 is 1, x squared minus 9. So you find f prime of x. Then we set it equal to 0. If I want to set this equal to 0, I have to factor it. I'm going to factor it as x plus 3x minus 3. Now I'm going to set that equal to 0, which gives me negative 3 here, positive 3 here. F prime equals 0. This results in negative. This results in positive 3. Now continue. So f prime is 0 or f prime does not exist. F prime does not exist. What is this? This is a Greek letter phi. In set theory, this is known as an empty set. It refers to an empty set. That means there is no solution. So why is that? F prime is a polynomial of degree 2 with the domain of all real numbers. So where f prime fails to exist? Nowhere, because the domain is also all real numbers. So we have two critical points. Can we use negative 3? Well, is negative 3 in between the given interval of negative 6 to 0? Yes. What about positive 3? Can we use positive 3? Is that in between? No, so we can't. So we write negative 3 is an element of the way you write it, everybody. This notation, which looks like an epsilon, is read an element of. That means negative 3 belongs to this set. Therefore, we will use it. Therefore, we're going to go back to the original function, evaluate it at. So now we're going to find number 2, f of a, f of minus 6, f of b, f of 0, and f of all the critical points. We happen to have 1, okay? So f of negative 3. By the way, you may have more than 1. It's important to check everything is within the given interval. So we are going to write the original function, f of x equals 1/3 x cubed minus 9x. We're going to put negative 6, negative 3, 0. We're going to evaluate them. So when we put negative 6, cube it is negative 216. Times 1/3 is minus 72. This is plus 54. And they add up to negative 80. We plug in negative 3, we get 1/3. Negative 3 cubed minus 9 times negative 3. And this is negative 27. 1/3 of it is negative 9 plus 27. We get positive 18. Now b is 0. Plug in 0, and clearly you can see you get 0. Now we move to the third step. Absolute max equals the largest value. So absolute max equals 18 at negative 3 comma 18. Absolute minimum is the smallest value, equals negative 18 at negative 6, negative 18. This is important, the way you write it. They may want the absolute max and absolute mean only, done. They may want it at just the x coordinates. You write x equals minus 3. They may want it at the pair. How do you answer it? Just read the question, answer it accordingly in order to receive full credit. Find the absolute max and minimum value of the function on the given interval, where the function f of x equals x plus 3 to the power of 2/3 minus 5, the interval of -4 to 5. So the very first thing is what type of function do we have and what is the domain of that. So we are going to rewrite this as the denominator is 3 here. So cube root of x plus 3 quantity squared minus 5. So this is elementary algebra. We should recognize that. So what type of function we have? So I want to remind you of the cube root function. Cube root function, the domain is all real numbers. So what is this? If you replace the x with x plus 3, it takes you to the left by 3 units. So this moves 3 units to the left. When you square it, makes the positive side larger and the negative side flips over. And then -5 brings it down by 5. It doesn't change the fact the domain is all real numbers. So this is a cube root function. The domain is all real numbers. So you write f if it is a cube root function is continuous from negative to positive infinity. When you say continuous, that means the domain. And it's continuous over the given interval of -4 to 5 because this interval contains the interval of -4 to 5. So that's the first one. Now the next part, we're going to move on and find f prime of x. To find f prime of x, we're going to work with this one, not this one. So this is 2/3 x plus 3 to the power of 2/3 minus 1, which makes it -1/3 times the derivative of the inside, which is 1, minus 5 gives you 0. In other words, 2/3 x plus 3 to the power minus 1/3 is f prime of x. I'm assuming no one has any problem with differentiation. And we want to move on to see where f prime is 0 or doesn't exist. We're going to rewrite this by taking this to the power of positive 1/3 and putting it in the denominator. So now you're dealing with a fractional form. A fraction is either 0 or doesn't exist if, so fraction a over b is 0. If a is 0, that means the numerator is 0. Fraction a over b is undefined if b is 0. This fraction has a numerator which is a number. Doesn't matter small or large, positive or negative. It can never be 0. The only way it can be 0 if it involves a variable. So f prime equals 0. There is no solution. Or you can write 5. Then you move on to the second part. F prime is 0 or f prime does not exist. F prime does not exist if the denominator is 0. Because a fraction is undefined or doesn't exist if the denominator is 0. So clearly this is easy. I hope you see that if I choose x equals -3 becomes 0. So there's really not much you have to do to solve it. The question is, can I use -3? And you check, is it in between -4 to 5? Yes. Therefore, you're right. -3 is an element of this domain, and therefore I can use it. Which means I go to the second step. I evaluate the function at a and b at -4 and 5, as well as critical points. There is only one critical point. That's the minimum. So we want to evaluate the original function either in this format or in this format. And I hope you see that this format is easier. So we're going to stick with that. So we start with -4 and we're going to put in. When I put -4, added to 3 is -1. What is cube root of -1, still -1. When I square it, I get +1. So I get 1 minus 5, which is -4. Now, I hope you see if I put -3 here, this becomes 0. So I get -5. What if I put 5? Let's try. When I put 5 here, 5 and 3 is 8. Cube root is 2. So 2 squared is 4. Minus 5 is -1. This is basic math. We are just evaluating the function at different points. And so having said that, we move to the third one. Absolute maximum is the largest. Since all of them are negative, -1 is the largest. So absolute max is -1 at this pair, 5, comma, -1. Absolute minimum is the smallest, -5 at this pair, and we write absolute maximum equals -1 at 5, comma, -1. Absolute minimum is -5 at -3, comma, -5.